Hi there, folks. Today we're going to start talking about some of the lines and segments that we deal with when we're talking about circles. And the first of those is a tangent line. Okay, so when we talk about tangent lines, a tangent line, basically when we're tangent to a circle, it's a tangent line if it only touches the circle at one point. In other words, it kind of glances off the side of this thing. So a line in the same plane as the circle that only intersects the circle at one point. And so when we kind of think about this, if I had a circle that looks like this, a tangent line would only touch at one single point. Okay, and so it kind of glances off the side. If you think about rolling a wheel across the floor would be a tangent line to that wheel. The wheel only makes contact at one single point at the very bottom of that thing. Okay, and so that's what we're talking about when we talk about a tangent line. It only touches the circle at one point, kind of glances off the side. The point where that thing touches is called the point of tangency. That's that intersection point between the tangent line and the circle, okay? So the point at which the tangent line intersects the circle, that's the point of tangency, okay? When we talk about tangent lines, if a line is tangent to the circle, the first theorem that we have here is that basically any radius or any diameter as well is going to be perpendicular to that tangent line at the point of tangency. So if a line is tangent to the circle, then the line is perpendicular to the radius at the point of tangency, okay? So we compare a tangent line and a radius or diameter. We could throw diameter in here. Okay, if we draw a radius or diameter to the point of tangency, we're going to form a right angle, okay, between the radius or diameter and that tangent line, okay? For example, if I look at something like this guy, it says find the value of x, given ML and MN are tangent to circle O. And so when you look at this, if I have circle O, right away, these are radii in here. So when we look at, OL, this is a radius, and ON is also a radius. And we know that because of just the definition of a radius going from the center to the outside of the circle here. Okay, so now if it's telling us that this guy is a tangent line over here, and this guy down here is also a tangent line, the thing that we automatically know is that these guys right here have to be 90 degrees. So that has to be a 90-degree angle. This has to be a 90-degree angle, okay? If I have a tangent line and I have a radius that goes to the point of tangency, it's automatically 90 degrees. And so now from here, what I can do is I can look at the shape LMNO. That is a four-sided figure, which means the angles inside of that thing are going to have to add up to 360 degrees, okay? And we know that because we could use our formula. You probably already just remember that a triangle adds up to 180, a four-sided figure adds up to 360. But if you forgot that, you could always do this formula of the 180 times n minus 2. Okay, so 180 times 4 minus 2 gives me the 360. Okay, so the angles inside of here have to add up to the 360 degrees. And so now I just have to solve this thing. So I combine like terms, that's going to give me a 297. Now I'm going to subtract that 297 from each side. And I end up with a 63, so 63 degrees. Okay? If I look at something like this guy, it says that DE is tangent to circle O. So once again, DE, this guy is a tangent line up here. So this is a tangent line. And if you notice, once again, what I have here is I have a diameter, all right? Or I could just think about the radius itself, the radius DO. OD is a radius because it goes from the center to the outside. And notice it intersects at the same point that the tangent line does, so that radius or that diameter goes to the point of tangency, which means then that this is automatically 90 degrees right here. So that has to be 90 degrees. And since what I have here is a triangle being formed, I know that the three angles inside of a triangle have to add up to 180 degrees. So the 90, the 38, and x all have to equal that 180. Okay? And that one we hopefully certainly don't need a formula for. The last one I can understand if you did. But right here, combine like terms. and subtract that 128 from each side. Okay, so x equals 52 degrees. All right, but again, that idea that the tangent line and the radius come together at a 90-degree angle if they meet at that point of tangency. Okay? The next thing we can talk about here is if a line in the plane of the circle is perpendicular to the radius at its endpoint, then the line is tangent to the circle. This is the same thing, but in reverse, okay? And so as we're looking at this thing, the previous one was, hey, the tangent line and the radius come together at a 90-degree angle if they meet at the point of tangency. And this one's just saying, hey, if one of these things meets on the circle at a 90-degree angle with a radius, well, then that line must be a tangent line, okay? So it's kind of just using the same thing, but in reverse. For example, if I look at something like this guy, it says find the value of the radius. And once again, we know that this is a radius. We know that BA is a tangent line or represents a piece of a tangent line because it's coming together with this thing in a 90-degree angle. And so there's a couple important things that happen here. As I look at something like this guy, notice I have a triangle that's formed here. So I do have a triangle that's formed. And it is a right triangle, which means I can use the Pythagorean theorem to find different pieces. However, I don't have this entire side right now. When you look at this guy, OA, I only have a piece of that. I only have this little piece out here, which is 8, okay? So what I need is the entire thing. Well, that other piece of this thing is the radius. So maybe I'll call it something like R. So here's a radius. This is also a radius. And now I'm going to do the same thing. I'm going to do the Pythagorean theorem, but it's a little bit more complicated this time because as I plug this in, look at the values that I get here. So it's a squared plus b squared equals c squared. In other words, r squared plus 12 squared equals, well, it's not just 8 over there. That entire side, OA, the entire hypotenuse there, is r plus 8. Kind of think about the length of that line, kind of using segment addition. Well, I want that guy squared, okay? So a little bit more involved than what we would normally have for something like these guys. But again, I just continue to simplify. When I multiply this guy out, r plus 8 times r plus 8 is going to be an r squared plus 16r plus 64, going back to my days of algebra here. And now I got to get all the r values on the same side, so I'm going to subtract the r squared from each side. Oh, sorry, I switched color schemes there for a moment. Okay, and now from here I do the same things that I would normally do to solve, okay? So now here I'm going to subtract that 64 from each side. I'm not going to write the minus 64 here. I'm sure most of us can do this at this point. So I subtract the 64 from each side, and now I divide by the 16. Oh, sorry, I wrote 16 instead of an 80 here. Oh my. Get your head in the game, Mr. Jansen. There we go. Okay, so the radius this time is 5. Okay? If I look at this one, it says determine if AB is tangent to circle O. And this is kind of more along the lines of what we were referring to in the theorem that we just talked about. The theorem basically saying that, hey, if I can show that these come together at a 90-degree angle, then I can say for sure that BA must be a tangent line or a tangent segment this time. Okay? And so when I look at this, once again, I'm looking at a triangle. And really all I have to say is, well, if I can find out if that is a right triangle, then I would know if that angle over at B is a right angle. And so really I'm just going to test to see if this thing is a right triangle. And so once again, I'm in that same situation where this is a radius of 7, which means this entire side is actually 32 when I go to look at it. And so now I'm just going to look at this thing from the perspective of the Pythagorean theorem. Remember, the converse of the Pythagorean theorem is, if I can plug these in and it works, I must have a right triangle. Okay? And so in the previous example, we said, hey, it's a right triangle. I can use the Pythagorean theorem. Well, now let's test the Pythagorean theorem to see if it's a right triangle. And so once again, I do something like this. I say, okay, a squared plus b squared equals c squared. And I just work to see if this is a true statement. I do the 7 squared and I get a 49. I do the 24 squared, and I get 576. And then the 32 squared gives me 1,024. And then, of course, the 576 and the 49 added together gives me a 625. Looks like I came up a bit short here. And so when I look at this thing, these are not equal, which means this thing is not a right triangle, which means that AB is not a tangent line. And when you look at it, just out of curiosity with the numbers here, if AO, if this entire thing had been 25, then this would work out because 25 squared is the 625, okay? And so this is set up for you to make the most common error, which is to assume that that 25 is the whole thing instead of that piece, okay? So don't forget to make sure you're looking at the entire hypotenuse here, which is that 32, okay? The last theorem we have here, of two tangent segments share an endpoint outside the circle, then the segments are congruent. All right, so in other words, if I have two tangent lines that come together at a point outside the circle, that distance from the point where they intersect to their points of tangency, they're going to be equal. Okay, so they're going to give us congruent segments. They're going to give us equal portions. Okay. And so when I look at something like this guy, it says find the perimeter of triangle ABC. So once again, if you kind of break this down into different tangent lines, if I were to look at just this piece of this tangent line of AD right here, well, here's another tangent line. AC is another tangent line that intersects there. If I just look at these guys, these two pieces that I've kind of colored in purple, this is what that theorem is saying. Those two pieces have to be the same. So I have two tangent lines that meet at point A. Well, the pieces, or the distance from point A to their points of their points of tangency have to be congruent, have to be the same. Okay. In other words, if that piece is a 10, well, then this piece over here must also be 10 centimeters, okay? But again, it's just that piece. It's not the whole way across AC. It's just to this point of tangency, okay? And likewise, if I look at any of these other guys, again, here's a tangent line and another tangent line that come together at point B, okay? If two tangent lines come together at a point outside the circle, it means that those distances from that point of intersection to the points of tangency are going to be the same, okay? So those pieces are going to be congruent. In other words, this little piece over here has to be 15 centimeters as well, okay? And then likewise, the last one down here, oh, I erased a little too much there. This last one down here, when I look at these pieces, again, they also have to be the same. It's two tangent lines coming together at point C, which means the distance from point C to the points of tangency have to be the same, 8 centimeters. Okay? And so as I kind of string all of this together, I can look at each side of the triangle now and say, well, this whole side over here, AB, has to be 25 centimeters. And this whole side over here, AC, has to be 18 centimeters. And this whole side over here has to be 23 centimeters. Okay, so now looking at the entire sides of this triangle, I can see that I've got a 25, a 23, and an 18. And so to find the perimeter on this thing, I'm just going to add those together. Okay, and when I do that, it gives me about a 66, it looks like. Okay, so the perimeter, I'm just going to say perimeter equals 66 centimeters. Okay. So tangent lines intersect the circle at one point. They glance off the side of the circle. What's special about those is tangent lines will always be perpendicular to a radius that meets at the point of tangency, or a diameter that meets at the point of tangency. Okay? And then the other thing we have here is that when two tangent lines intersect outside the circle, those pieces that connect from the point of intersection to the points of tangency are going to be congruent. They're going to be the same distance. Okay?